I'm Colton Karosik, and we're gonna be. This is Carlos Coe's Exam 1, Part 3, and we will be deriving an expression for density of a perfectly cylindrical wooden log of radius r floating in water on its side that extends a maximum distance h above the water level. So, first thing we do is we draw the log. So it can be represented. H here, it's bad. So this is where the water comes up to. On the log, and we have h height above, and this is the radius to the center of the log. And this here on the bottom is the length of it. So we assume that the velocity is equal to 0. That means that the acceleration is also equal to 0. So this allows for the buoyant force to be equal to the weight of the log so that it stays even. And then that equates to, in symbol terms, the mass of the water times gravity is equal to the mass of the log times gravity, and the g's can cancel out here. So that's just our givens. And that leads us to, we have the density of the water times the cross section of H2O at the level, up to the level. We can represent this by this times the length. So this here times the density times the length is equal to the density of the log, which is what we're trying to figure out. Times the equation for a circle, pi r squared times length. And then if we break this down to kind of look at the shapes and what we want to find, this here, the bottom half, is equal to circle minus top half. I wouldn't call them halves, but sections. And then the top section is equal to this cone. Cone will be the simplest way of us to look at this. Cone minus this here triangle, which we can calculate. And then this will be the cross-sectional area, as I explained earlier. All of this times length times density of this. So if we look, we can kind of see the things we want and kind of blow them up here. So we'll have, that's the level, then we'll have, whoop, I crashed. It's all good. You're gonna let me move, right? Okay. We're not gonna worry about that. We got space for now. That's cool. We have, cool. This is a little bigger. This is a little higher. So this is our height. And then we have radius. Come on. Close enough. Radius. And then this here distance that I'm kind of making bold can be represented as radius minus height. And then if we were to make the triangle, we're going to put another one here. Come on. And so we are, of course, and we can represent these angles by theta. These angles are going to be important to be able to solve the triangle and find the measurement we need. And they're the same, theta and theta. And then we're going to take 2 times this, 2 times that angle to get one angle, which is 2 theta. 2 theta over the number of radians in a circle, which is 2 pi. Carson, I'm doing homework. Times the area of the circle. Pi r squared. And then we can see that these 2's cancel and the pi's cancel. So it leaves us with theta. Theta r squared. And then we can use trig to solve this identity, and that will give us theta equals arc cosine of r minus h over r, which is the identity of adjacent over hypotenuse. And we plug this in to theta. So you see we have adjacent over hypotenuse. So then when we plug that in, we get arc cosine r minus h over r times r squared and then we want to solve for the overall area we have, so go 2 times 1/2, which will immediately cancel, base times height, which goes to, and we're going to call these sections here, x, as our base, or however you want to look at it, should be really our base. X times r minus h and to solve for we use the Pythagorean theorem. X to solve for x, because we don't know what x is. X squared plus r minus h squared equals r squared. So you see that here. And this goes to x equals square root r squared minus r minus h squared, which simplifies to negative 2rh minus h squared, and then that's our x, of course, and we can then plug that back into here. So this is solving for our triangle, of course, equals r minus h times square root r squared r minus h squared. It's back. You do that to me. And then you have so this is our triangle, and based on these identities here, we want to subtract that from this here. It's the best identity that we have here for the total area of the circle. So we'll have r squared cosine arc cosine r minus h over h over r, sorry. A little too similar. Minus our triangle. So it's circle minus triangle to get our area above the water. I don't know, it's not copying. I will write it again, that's alright. R squared minus r minus h squared Sorry, I completely skipped my simplification. This is negative 2RH minus h squared. Negative 2RH minus h squared. R minus h. I'm writing too big. I can't see everything. Crap. So now I want to introduce the density of water in order to solve for the density of the log. So for every cubic meter is 1,000 kilograms of water is the ratio for the density. Meter 1,000. So we'll have the area of the circle, r squared minus r squared, r cosine r minus h over r. Times 2r h minus h squared r minus h, and I'm going to times this by 1,000. It's getting too big again. And divide it by the area of the square. The area in squared, whatever. We're using inches, meters, pi r squared. And that is our final equation, which will give us density of log, aka rho L. Thank you.